degrees in software engineering and maths. And well, his research predominantly focuses on computationally challenging problems in actuarial data science. So welcome, Patrick.
Thanks very much, Kasia. So today I have the chance to present a little bit of short work, joint work, mainly Eric's first project from his PhD, and joint work with Benjamin and Bernard. In this short time, there was more of an introduction to that work rather than a fully going through it. And because on Friday I bought a car and thus had to buy car insurance, I decided to focus on car insurance. My car was very cheap, but the car insurance really ripped me off. It was so expensive. Anyway, so I'll use just this example of car insurance. You could use any GI for this kind of application. Okay, so what does it mean for you to have a claim size prediction, say, machine learning model for car insurance? So if you ask the computer scientists about this, they'll look at the inputs. Say you have some covariates, driver age, car age, type of the car, and your model would just be spitting out a single number, and that might be your best guess of how expensive the claim would be to the repair costs, right? So these single output machine learning models are very simplistic, and from the perspective of imagine trying to tell someone, right, the next time you have a car crash, it's going to cost exactly $12,133 to repair that car crash. I mean, that's insane, right? There's so much variability in this kind of problem. So that's a deterministic model, and so I'm going to move over to talking about probabilistic models now, and that's this field called distributional regression. And what that means is that for each different customer, say we have customer one here has these characteristics, the output, the claims that are generated, we know that they're within some range of outcomes. So it's more likely to be here, less likely to be down here. And then for each different customer, we get a different probability distribution that's being spat out by the machine learning model. So that's what distributional regression is. And I mean, we want to do this for lots of reasons. I mean, actuaries want to know what sort of average price of a claim maybe, wants to do some risk management and look at the quantiles or look at how the deductibles affect the policy. So having the whole distribution is super useful. And we kind of do this already, actually. We don't think about it, but a GLM is a distributional regression technique. Let's say, for example, gamma GLM locally. That's for each individual policyholder that spits out a new gamma distribution, whose mean is specified by this linear form with the exponential function. And there's a lot of great things going on with this setup. Right? It's very simple, easy to train, easy to interpret. But from the distributional regression perspective, it can be bad at regression and bad at distributional regression. So bad at regression, I mean that the relationships between the inputs and the target can be too simplistic, and the distributions that you slap on the output there can be too simple as well. So here, basically, we come up with a guess of the average claim and then just whack on some kind of distribution without thinking too much. Right? So what can go wrong? Say we have a complicated relationship between one of the features and the target. Let's just pretend driver age has this kind of impact on the average claim size, so that young, people in their mid-30s have a very low claim sizes on average compared to the younglings here and these old people here. So GLMs, right, we have the linear relationship, can't easily handle this kind of this data. So there's one reason why we want to use a neural network. It's a king of representation learning. So you just throw the data in and it figures out all the nonlinearities in there. Another example, focusing on why the output distribution can be too simple, is multimodality. So this is, say, one specific car's risk profile, if you like, where in that household there's a parent and a kid, both share the car, and they have different risk profiles themselves. So the parent is very safe. No, that's not the right one. The parent generates a distribution like this of plane sizes, the blue curve, whereas the kid driving is of course reckless and generates larger planes. But from the insurance perspective, they get a mixture of both of these drivers. So there's this red distribution here that they really is the real conditional distribution that needs to be estimated here, which is too restricted for a GLM. So there are lots of solutions already to this problem, and some of the people in this room here have contributed to them. So the GLM already talked about a fair amount. The combined actuarial neural network, Mario's creation, is a way to take the GLM and you add a neural network to it so that it will adjust the output distributions, pick up all those complex non-linear relationships, and that kind of fixes the problem of the regression side of why GLM is bad, the input mapping. But it doesn't address the output distribution not being very flexible. One work that based on Bishop and Bernard has also worked on this as well is a mixture density network. That's a neural network where every time you put in someone's information, it spits out a mixture distribution, just like this one here. That gets you some of the ways of solving this problem. They're a bit hard to train actually. And the very last one here, deep distributional regression, just goes away from having any parametric families at all in the output. It just sort of spits out a non-parametric distribution, which is the most flexible thing that you can do on the output side, but it's very little interpretability attached to that. Okay, now on to my last slide, just to advertise what we have produced, called the Distributional Refinement Network. The main thing here is to match a neural network with a simple model. So we'll say a generalized linear model, just to keep things simple. And then we train a GLM, and we train a neural network that improves the GLM. So when we come to make a prediction, we pass in someone's characteristics. We look at the density that the GLM generates, and then the neural network refines that. It adjusts it. So maybe it says, okay, this is the whole mean is too low, or maybe we need to increase the tail a little bit, and we'll make these small adjustments. And it's kind of like a cosmetic surgery for your GLM, right? You can do a little bit of change or large changes. That's why I say it kind of like you can either have Botox or a facelift, right? That's what the DRN allows you to have this lever that says my output should be very similar to the GLM, and trust neural network, or they can drift further away. And I won't be able to say anything about how this works. It's all in the paper or in the Python package. Thanks very much for your attention.
Any questions to Patrick?
Thanks for your talk. I was wondering how the distributional refinement network actually improves on the GLM. Which hidden features does it capture that in the normal estimation process of the GLM does not capture?
So it's mainly those two aspects that I mentioned. So the neural network, it takes in our data here, and it does a lot of advanced processing of the input. So it can do a lot better job than just a bunch of linear combinations of the features, for example. And I mean, the superpower of neural networks, in my view, is it can also handle image data and text data. I think that's the killer application of neural networks, all those things as well. And then the totally flexible output distribution as well. In the GLM, you're stuck with exponential families, basically.
That's the distributional refinement model, right?
Yeah, that's what I'm about to say.
Any other questions? Like the distribution you have shown with like bimodal distribution where parents and kids are driving, generally parents don't disclose the kids driving the car, I think, to avoid the increase in premium. And some men don't report their wives driving the car, for example.
It changes the excess on the policy. The insurers make sure that it happens.
Well, I heard this from Julian Trufant, that you can see this in the data actually, this mixture of kids and risk for individuals. That's where I go there.
Any other questions? No? Okay, cool. Thanks so much, Patrick. Thanks. So we're coming to